Okay, bismillahirrahmanirrahim. For a first order reaction, this will be the last one, okay? Then kita done with this determination of order, kita boleh proceed to collision theory later on. Okay, for a first order reaction, T half is independent on the initial concentration A naught. Okay, so half-life method, macam separuh hidup, separuh nyawa macam tu kan, half-life method. But with respect to concentration, half-life means ini dah skip ke? This one. Okay. Half-life, okay, T half, where we can represent the half-life as T half. Okay, for a reaction is the time taken for the concentration of a reactant to drop to half of its initial value. Okay, all right, so with respect to half-life in reaction rate, half-life means time taken for the initial concentration to become half of its initial value. Okay, all right, so we know that initial concentration is this. For example, this is our initial concentration. So we want to know how long does it take for this initial concentration to become half of it. Jadi separuh. Okay, so berapakah masa yang diperlukan? So this is what we call half-life. Okay, this is what we call half-life. So macam biasa, even for the half-life, kita ada kategori, we have zero, we have first, we have second. And of course, they all have their own formula of half-life. Okay, alright, so this is the definition of half-life. Okay, so for zero order, guys, this is the formula. T half is equal to A naught divided by 2. Okay. Alright, in the first place, macam mana dia boleh dapat this formula of half-life? Okay, it's actually was derived from integrated rate law. Remember, zero order punya ni, apa zero order punya? So A at T time ni, maksudnya dia nak tahu berapa masa yang dia ambil kan untuk dia jadi separuh. Maksud divided by 2. Okay, this will be T half. So you rearrange everything and you will end up with this one. Okay, so this one is derived from the integrated law of zero order. Okay guys, so kita stop sekejap, seminit, 2 minit sebab azan dekat tempat saya. Okay, so kita stop sekejap. Come back to this later. Alright, so let's continue. Yeah, this one, this half-life formula is derived from the integrated rate law. Okay, alright. So again, we have graph to represent this half-life, but this time around, look at the graph. Look at the axis. Okay, so this time we use concentration versus time. Okay, concentration versus time. Bukan like integrated rate law tadi. Okay, and then after all, you perasan tak untuk first zero order ni, dia punya graph dia memang concentration versus time. Okay, yang kalau dia punya integrated rate law pun dia concentration versus time. Macam normal graph yang kita prepare untuk find out the rate and whatnot tu. Okay, dia sama. So concentration versus time. Why do we need to use concentration versus time? Kenapa tak? Why can't we use the graph from the integrated rate law? Sebab kita just nak tahu the half-life concentration di mana the initial concentration become half of the initial value. Itu je kita just nak tahu. Contohnya, macam mana kita nak translate the half-life. Okay, alright. So ini graph kita. Okay, ini graph kita untuk zero order. Okay, untuk zero order. Katakanlah the initial concentration yang dekat graph ni, dots dekat graph ni, okay, the initial concentration will be 0.2. Half of 0.2 will be 0.1. Okay, alright, macam ni. 0.2, okay, time dia 0. And then half of 0.2 will be 0.1 kan? Separuh daripada 0.2 will be 0.1. Okay, dia turun separuh kat sini, and then what you need to do is you kena pergikan dekat graph tu. Okay, mesti kena touch the graph sebab graph dots ni yang represent the reaction. Okay, so you 0.1 and then pergikan dekat graph dekat sini. Okay, turunkan dekat sini so that we can determine the time. So how long does it take from the 0.2 to become 0.1? How long does it take? It's 30 seconds. Okay, 30 seconds. So that will be the first half-life. Okay, that will be the first half-life. Okay, so daripada kita punya formula here, kita boleh relate banyak benda yang kita boleh discover ataupun translate that the T half is inversely proportional to K. Okay, when K increases, the T half decreases and vice versa, and it is directly proportional to initial concentration. When initial concentration increases, T half increases. Kalau initial concentration decreases, T half akan decrease. Like what we have here. Okay, alright, so 0.2 jadi 0.1. So katakanlah dia punya initial concentration sekarang adalah 0.1, katakanlah. Okay, 0.1, kalau half of 0.1 will be 0.05, betul tak? So 0.1 which is here just now, 0.05 which is half of 0.1, kita kena further lagi ke sana, jumpakan graph tu which is here, dekat sini. For the second half-life, berapa masa yang dia perlukan from 0.1 to become 0.05? Berapa masa yang dia perlukan dekat sini? So, kat sini berapa tadi? This is like 34 ke? 34 ke kat sini?
34.
34 Yang ni maybe around 52. So, you 52 minus 34 lah. Berapa masa yang diperlukan? As you can see, dia berkurang. Nampak tak? Kan kita baru translate tadi, kalau initial concentration decreasing, the T half will also decrease. You can also try out for the third half-life. Maksudnya kalau 0.05, separuh daripada 0.05 will be 0.025, which is around here lah katakanlah. This is 0.025. Okay, further lagi ke sana. Alamak, terlajak sikit. Ke sini which is here. Which is here, dia punya ni. So kat sini. Okay, yang ni tadi yang 0.05 just now kan. So here. So this is 52, this is 60. 60 minus 52, berapa masa yang diperlukan daripada here ke here. This is the third half-life. So 8. Okay, alright. Ini tadi berapa? Berapa jawapan? 12 tolak 4 jadi 8 12 tolak 4, 8 kan?
Yes, 8.
18. This one 30. 30, 18, 8. So dia decreasing. Okay, ini kita boleh expect sebab kita boleh learn this one from the formula of T half itself. Okay, but what we can confirm for zero order, the first T half is not the same as second T half and it's also not the same as the third T half. Dia tak sama, nampak tak? Berbeza-beza. 30 and then 18 and then 8. Okay. For zero order reaction, T half is directly proportional to the initial concentration. Okay. Alright, so let's look at the first order reaction. So boleh hafal formula of T half untuk zero order E0 over 2K. Okay. Okay, now first order pula. Like I said, first order ni, this is the formula. Ini. This is the final formula for T half. So how did we get this final formula for T half? Like I said, using the integrated rate law, kita masukkan the value. The value A at T time will be A0 divided by 2. Separuh masa dia tu. Separuh concentration dia tu. Okay, and then kita rearrange everything. So this will be the final formula, 0.693 over K. So this is already constant. Maksudnya apa-apa pun kita akan pakai 0.693 over K. K constant, this one is also constant. Maksudnya kita akan dapat T half yang constant if it is a first order reaction. Tadi kan tak constant. Perasan tak this one? This one tak constant. Dia berbeza-beza. First dengan second lain, dengan third lain. But for this one, remedial yang dia akan sama. Okay, maksudnya first T half would be the same as second. T half would be the same as third. T half. Macam mana boleh tahu? See, nampak dekat sini. Okay, sebab 0.693 is a constant value. And the K is known as rate constant, which is a constant. Okay, so the whole thing ni, for that particular reaction, will produce a constant value. For T half, you bagikan ni, you akan dapat T half yang sama. That's why you akan dapat this relationship. It's a constant. But this is the formula. Okay guys? Okay. Okay, contoh. Iodine is a radioactive isotope that undergoes first order reaction. So see, they mention first order reaction. So terus straight away use the formula for first order reaction untuk half-life. Okay, dah mention it is first order. Determine the half-life for radioisotope iodine 131. So yang kita tahu, yang kita ada idea first order, it will be a constant value. It's just that we do not know what is the T, what is the half-life. Kita nak kena determine that. Okay, but we know that it should be constant. But the first order. Okay, alright. Okay, this is the graph, example of graph for first order. Okay, first order. As you can see, nak determine half-life untuk, even for first order, kita boleh determine by using graph concentration versus time. Tak payah pakai integrated. But apa yang kita nak adalah concentration. Half-half kan concentration dia tu. Okay, alright, katakanlah. So this is the graph provided. Concentration versus time untuk first order. Okay, initially the concentration is 16 molar. okay, is 16 molar. So half of this concentration will be 8. Okay, ini yang dah memang touch the graph. Okay, so 8 adalah separuh daripada tu. Okay, pergi ke graph tu. Mana? Mesti kena touch the graph. Okay, this is the point. Okay, alright. So ini initial tadi 0 kan? Okay, so this one is the half. Maksudnya separuh daripada 16 tu, 8 here. Okay, alright. So how long does it take from 0 to here? Okay, alright. Itu yang first half-life. Katakanlah you nak cari the second half-life, kata starting from 8. So half from 8, ini lebih kurang berapa ni? 8 ke? Okay, lebih kurang 8 ke macam tu kan? 8. Lebih kurang lah saya baca sebab based on dia punya scale.
8 madam.
Lebih kurang Okay, so separuh daripada 8. So assume this is the initial sekarang. So half of this initial will be 4. Betul tak? Okay, jalan kan, make sure dia kena touch the graph. Touch the curve, the line tu. Curve tu Alright, so here. So here. So ini tadi you punya initial, yang initial. Jangan pergi kat sini. Ini initial yang paling awal-awal. Ni yang first half-life. Second half-life, you punya initial will be this one. Kan? Dia punya time dekat situ. So this is 8. 8 kepada berapa ni? 16.
16.
This is 16 kan? So 16 minus 8, you akan dapat 8.
8.
So you 8, sini pun 8. Nak buat lagi? Buat. Separuh daripada 4. Berapa? 2. Jalankan dia. Di sini. So turunkan. So tadi yang ni yang initial kan, yang 4. 4 tu initial, so half of it will be 2 which is here. So turunkan. So from this one to this one, you dapat berapa? 16, sini around 24. 24 minus 16, you akan dapat 8. See? 8, 8, 8. So the constant first T half there is the same as second T half and also the same as your third T half. Okay, alright. So what can we conclude from that? For first order reaction, T half is independent on the concentration. It is not dependent on the concentration of the reactant. Okay, that's why T half is constant. This is opposite to zero order. Zero order, it depends on the concentration. Okay, look at the formula. From the formula, you're still able to determine that relationship. Okay, so two characteristic of first order. Okay, all right. Second order, guys. Okay, this is a formula of second order. 1 per Ka naught. 1 per Ka naught. So you tengok beza kan dengan okay, first order senang lah. Tak payah pening kepala. Okay, zero order yang leceh sikit dengan second order. Tapi zero order tadi, kalau saya nak, kalau dah lang kita baru belajar kan, terus try lah, cuba ingatkan. Tadi berapa? Concentration dekat atas yang saya ingat, bawah 2K. Okay, A0 and then 2K. So dia kan opposite. A0 kalau second order dekat bawah. Kalau kat bawah, that means dia inversely proportional dengan time. But this one, dia dekat atas. This one is directly proportional, but inversely proportional to K. Ini sama. K dia still sama, dia inversely proportional, but concentration, okay, dia tak sama, dia opposite. Okay, alright. So cara dia still sama. How would you determine it? Okay, by using graph. Graph dia, concentration sama juga, concentration versus time. Okay, for second order, you akan nampak pattern dia macam ni. Okay, you boleh nampak pattern dia. So kalau kita nak baca from the formula, what can we conclude from the formula? Cuba kita conclude. So, kalau A0 decreasing, kita go for decreasing lah sebab dia graph dia kan menurun kan. Okay, if A0 decreasing, the initial concentration decrease, the T half will increase. Dia opposite pula. Okay, the T half will increase. Cuba you provekan this statement from the graph. Macam biasa, macam yang saya ajar tadi. Okay, alright. So, saya cut short ya. Okay, so this is your first half-life. This is your second half-life. And this is your third half-life. As you can see, dia makin lama, makin longer. The time taken for the half-life for second order reaction is getting longer. Makin lama, nampak tak? First half-life, second half-life, third half-life. See? Which is opposite dengan zero order just now. Dia makin lama makin cepat. Zero order tadi. Makin lama makin cepat. Tapi second order makin lama makin lama. Sebab apa? Inversely proportional. Okay? Alright. Okay. Cuba tengok example. Okay, I don't think the question is that difficult. Okay, complex sangat ke? Tak sangat. Sebab what you need to do is to apply the apa nama tu, the formula lah. Okay, sebab kalau jenis-jenis soalan macam ni, soalan kena provide the order. Okay, tapi kalau with respect to our focus nak determine the order of half-life, nak determine the order of reaction by using half-life, you must be able to read the graph. Dan you kena tahu pattern dia begini. Yang pattern like what we have discussed just now. You kena baca from the graph, you tengok pattern dia. Dia getting longer ke? Is it constant ke? Is it getting shorter? Kalau dia getting shorter, oh, this is zero order. You determine sendiri benda tu. Okay, that's why we can use half-life to determine the order of reaction. Okay, tu fokus kita sebenarnya. Tapi yang soalan-soalan ni hanya terbitan-terbitan sajalah other than asking determination of the order of the reaction. You can also be asked related to half-life. Okay, related to half-life where you have to apply the formula. Okay, contohnya decomposition of ethane to methyl radicals has a rate constant of this. See, rate constant of this. Maksudnya you have to calculate the half-life of the reaction in minute. Calculate the half-life. Okay, kita ada 3 jenis half-life. Zero, first dengan second. Nak pakai formula yang mana? Kita kena tahu order dia. Okay, alright, that's why dia bagi unit dia bagi rate constant with unit there. So that you'll be able to determine the order. Dah tahu order guys, masuk je formula. Masuk je data dalam formula. So the rest settle. Okay. Yes, question? Okay. Ada soalan ke? Alright, kalau tak ada soalan, cuba
nak tanya.
Ya.
Maksudnya kalau yang kan yang half-life yang untuk second order reaction ni, so maksudnya dia punya masanya lagi panjang, so initial reactionnya lagi sikit lagi masa panjang lah, maksudnya macam tu.
Initial reaction.
Initial concentration.
Initial concentration, kalau kita relatekan dengan initial concentration, makin sikit, makin panjang. Kan? Dia kan inversely proportional kan? So, the decrease in initial concentration will cause the time taken, the half-life, okay, will be longer. Betul begitu. Okay? Which is opposite dengan zero order kan? Zero order, dia decrease in concentration will also decrease the time taken. And this one, the opposite. Okay? Faham ya? Okay kan yang tanya soalan tadi siapa?
Faham, madam.
Okay, alright. So, you guys try buat this checkpoint 6. Okay, I need to go to the toilet first. Try buat, maybe boleh proceed. Kalau dah siap, okay, you may proceed to checkpoint 7. Okay, kita buat dua checkpoint je lah, and then the rest tu please do it on your own first, and then we will discuss next week. Okay, kita nanti sebab kita nak masuk new topic lah, new subtopic. Okay, alright, try to do it first. Kita discuss after this. Okay, I need to go to the toilet first. Okay, so let's discuss the answer. Okay, checkpoint 6, guys. Question 1. Cyclopropane is the smallest cyclic hydrocarbon. It undergoes rearrangement to produce propene at 1000 degrees Celsius as shown in the following reaction. If the rate constant is this, okay, determine the half-life of the reaction. Okay, so what is the order of this reaction, guys?
First.
First order.
First order.
First.
Alright, okay, thank you. So it is a first order reaction. So once you dah tahu the order of the reaction, you can just straight away use the formula of first order. Okay, so you have to find the half-life. So the formula of half-life will be terus hafal jangan buang masa. Yang mana yang you boleh terus hafal, you terus hafal. Nanti bila nak exam, tinggal nak flip saja, nak recall balik. Bukan time tu nak kena buat kerja-kerja berat. Alright, so 0.693 0.693 kalau nak lebih, kalau takut dengan value ni, maybe you can use ln 2 over K. Okay, alright, so over 9.2 as negative 1. Okay, alright, so this is the formula. Calculate the time taken for the concentration of cyclopropane to reach 1/4 of the initial value. The time taken again. Okay, alright. So for this one, you may use two methods in order to solve for this one. Okay, you may use the integrated rate law, the formula of integrated rate law, or you can also use the half-life method. Okay, alright. So let's see if you choose to use integrated rate law for first order. Okay, so first order we know that we're going to be using the ln A at t time is equal to negative kt plus ln A naught. Alright, so kalau nak cari t, ni nak cari. So the rest should all be known value. Kita kena dah ada dia punya information so that we can find out the t. So k is not a problem. A at t time dengan A naught. Because what is given to us, dia bagi sebenarnya, it's just not directly. Okay, alright. So for the concentration of cyclopropane to reach 1/4 of the initial value. 1/4 maksudnya 1/4 daripada initial value dia. That means the initial value will be 1 lah here. Okay, dia nak maksudnya yang tinggal nanti tinggal 1/4 maksudnya 1/4. 1/4 is equal to 0.25. Okay, alright, so you selesaikan lah. K ni dah boleh masuk lah value dia. Okay, alright, so itu cara using the integrated rate law. The other way is by using the half-life method, because half-life method dia, sebab kita tahu this is first order. That means dia punya half-life dia constant. And we know that initial concentration will be this one kan. Katakanlah this is the initial concentration. And then half of this initial concentration will be this one. Divided by 2. Separuh daripada this one will be over 4. Which is 1/4 darab A lah. Betul ke tak betul? So kita nak so kita nak kena tahu this, ini berapa, ini berapa. And then kita tambahkan dia, dapatlah value dia. Kita tambahkan ini berapa time dia. This is the first half-life. This is the second half-life. Once kita tahu this one, automatically we will know this one and we can just total up and we will get the time taken for the initial concentration to become 1/4 of its initial value. Okay, alright. Inilah, ini masuk je half-life. Okay, yang contoh dekat sini dia bagi cara half-life. Okay, cara half-life. So like I said just now, half of it you would require this one. So kalau you further dia punya half-life, okay, for the second half-life, which become 1/4, so you times 2 lah, 0.075 times 2, you will get 0.15 second. Okay, question 1, checkpoint 7, question 1. The reaction of 2-methyl-2-bromopropane with aqueous sodium hydroxide is first order. Asyik first order Okay, dia ada dua reaction. Sabar. Okay, it's first order with respect to 2-methyl-2-bromopropane and zero order with respect to the OH minus ion. Alhamdulillah. Okay, all right, and then we have the equation. So as you can see, we have two reactants that, and then the order for each reactant is also stated in the question. Okay, so given the rate constant, yeah, all right. So maksudnya, with respect to hydroxide, this one first order. Okay, all right. This one zero order. Okay, let's see if we were to write the rate law lah. The rate law is equal to K CH3 BR. Ada C kat dalam tu. Okay. This is here.
Yang ion hydrogen tu and hydroxyl tu zero order.
Terbalik Sekejap. Zero order. Okay, kita balik. Sorry. First, this is you. Okay, betul. Okay, terbalik Alright, so this is first order and this is OH minus is zero order. So sebenarnya rate is equal to K okay, because this one is equal to 1. Alright, so the overall order for this reaction will be 1. Because 1 plus 0 is equal to 1. Okay, alright. So dia akan based on overall order. Kita punya order, nanti kita nak pilih, nak formula apa kan, kita akan based on the overall order. Bukan based on 1 dengan 0, nanti banyaklah kerja kat situ. Okay, alright. So given the rate constant is, ialah asyik first order dia. Okay, betul lah, barulah boleh cakap first order. Okay, so first order, and then it is proven based on the unit of the rate constant here, minute -1. Calculate the half-life for the reaction. Okay, ni like what we had calculated just now, exactly the same using the same formula. Okay, so you can simply you can calculate the half-life for the reaction. Okay, masukkan dalam formula je. Then B, calculate the time taken for 60% of 2-methyl-2-bromopropane to be reacted with OH minus ion. To be reacted. Maksudnya dia akan react dengan OH minus ion. So imagine berapa yang tinggal. Okay, fahamkan statement tu betul-betul. 60% to be reacted. Maksudnya dia nanti akan react dengan OH minus. So what is left would be 40%. 40% of 2-methyl-2-bromopropane. Untuk soalan ni. Okay. Nanti mungkin dia ada jenis soalan lain, tapi maksud dia tu memang maksud dia yang tinggal adalah 60%. Maksud dia. Tak tahu, saya tak boleh nak kata dia akan keluar macam mana, but please read the question carefully. Okay. Alright. Yang ni kita boleh pakai integrated rate law lah. Okay, boleh pakai integrated rate law. So jom tengok jawapan dia. Okay, alright. So that is half-life. Secondly, using the integrated rate law for first order, dapatlah the value. Okay. Alright, so kita stop dekat checkpoint 7. So the rest of the checkpoint will be discussed next week. So that kita boleh proceed to the next subtopic. Okay guys. Alright, maybe I can conclude further here dekat sini. Okay. Okay, try to complete all the checkpoints. And this is a summary of the kinetic for reaction of type A producing product that are zero first or second order in concentration E. Okay, alright. This is the summary lah, senang cerita. Ini conclusion yang kita dapat from so far that we have learned related to determining the order of the reaction. Okay, alright. Kalau zero order, rate law dia, how do you write the rate law? So this is how you write the rate law. So this is subject. okay, we subject to this reaction A producing product. So kalau if we have more reactant, that means ada pertambahan lah dekat sini. Okay, we have additional of reactant in the rate law. Okay, integrated rate law. Okay, so dia dah sum up, dia dah kumpul. Okay, all the integrated rate law, and then linear graph. Linear graph, again for the integrated rate law, kalau dia adalah that particular order, so you akan dapat linear. Ya Allah, apa nama ni, saya punya apa, mouse saya ni kan. Ini semua membuang masa benda-benda macam ni kan. Okay, concentration versus time, you kalau zero order, kalau first order you should get ln concentration versus time. But for second order you kena dapat 1/A versus time, the linear graph for this one, this graph. Okay, macam ni lah rupa dia, begini ni kat bawah graph ni, graph di bawah ini ya, example. Even the slope is also given. Okay, unit of rate constant, half-life, the formula of half-life. Okay, alright, so this is the summary for topic 1.3. Ya, baru topic 1.3, kita ada sampai 1.7. Okay, 4 more subtopic to go. Okay, right. Okay, so now let's proceed to 1.4, the collision theory. So as you can see, the learning objective for this subtopic is also a lot. Banyak juga dekat situ that you need to make sure that you cater all of this once you have completed this subtopic. Okay, alright. Collision theory. So sedikit sebanyak we have I have told you, we also have discussed related to this collision, okay, earlier on. So you dah ada that idea tu dah ada lah, okay. So basically for a reaction to take place, they need, the reactants, the particles, the molecule need to be collided with one another. Okay, they need to collide so that it increase the probability of producing product. Probability, I'm using the word probability because not all collision produce product. Okay, alright, so the basic principle of collision theory is that particle must collide effectively. In order to produce product, the particle must collide effectively in order to form product. Kalau dia collide saja, that means itu probability of to produce product may increase. Tapi kalau dia collide effectively, that means confirm it will produce product. Okay, so the rate of reaction is proportional to the number of effective collision per second among the reactant molecules. So the rate of reaction sebenarnya depends on the number of effective collision. Effective collision is again the collision that produce product. Okay, alright. So what is effective collision? Like I said, collision yang produce product, okay? An effective collision is one that results in the formation of product molecules. Only a small fraction of collision lead to a net change in ordinary condition. Sebenarnya collision, banyak sangat berlaku, okay? Tapi effective collision is nak kata rare, bukanlah rare kan, dia depends on the condition of that reaction. Okay, so in order for a collision to be effective, the reacting molecule must, okay, ada dua syarat yang dia kena obey in order to have an effect. Sorry, tersembur. Okay, so seronok sangat bercakap sampai tersembur. Minta maaf lah atas kejadian tadi, okay? Alright. In order for a collision to be effective, the reacting molecule must collide in the correct orientation. So ada dua syarat, there are two rules for a collision to be considered as effective collision. First, okay, the they must collide in a correct orientation. Pelanggaran tu mestilah orientation dia dalam keadaan yang betul, correct orientation. That's why, like I said just now, dia bukan semudah berlanggar saja. Okay, so it need to be collided in a proper orientation. Macam jodoh kan, dia bukan sekadar berjumpa saja, dia kena ada barokah dia kena ada keberkatan dia kena ada memang jodoh awak. Contoh. Okay, macam ni lah, dia bukan saja berlanggar, dia kena correct orientation, guys. Okay, right. Secondly, they must possess energy equal to or greater than activation energy ataupun EA. Okay, activation energy stand for EA. Alright, so they must have they must have sufficient energy lah, senang cerita. Okay, they must have sufficient energy in order, the energy is needed in order to form bond ataupun to break the bond. So kalau this molecule do not have sufficient energy, macam mana nak form bond, macam mana nak break the bond kan in the first place. So that's why second point would be possess energy equal to or greater than activation energy. So these two is very important. Katakanlah in exam, okay, you are asked to list down the factors that affect the effective collision ataupun yang sewaktu dengannya lah. Okay, proper orientation, they must collide in proper orientation and possess energy equal ataupun greater than activation energy. Remember, activation energy is, this is the profile energy diagram. Okay, alright. Yep, the bouquet. This bouquet is what we call EA. They must, okay, the molecule need to have sufficient energy in order to daki this bukit and overcome this bukit and finally turun ke bawah ini and produce product. If they don't have this sufficient energy, macam mana nak produce product? Okay, macam mana nak produce product? In a way, that energy is needed to form a bond, to break a bond. Okay, so itulah kegunaan energy tu. So dia kena possess this energy, this amount of energy. Okay, right. So let's look at in terms of orientation. What does it mean by orientation just now? Proper orientation. Okay, so consider this reaction, NO2Cl plus Cl to produce NO2 and Cl2. Okay, the orientation of the collision cannot produce a Cl2 molecule. Okay, we have two types of collision. One is of course the ineffective collision. The other one is effective collision. So how do we differentiate these two? Okay, so the first one is ineffective. Why is it ineffective? Kita cakap dia ineffective kan, but we have to know why is it ineffective. Because the orientation is not correct. So how do we know that the orientation is not correct? Okay, alright, so the best way is to refer to the equation. Okay, kita punya tips adalah refer to the equation given. Okay, so this is the NO2Cl. This is the Cl. Okay, so kita nak produce apa? Kita nak produce Cl2. Tadi Cl2 single je. Now later as the product we want the Cl2 to be formed. Maksudnya kalau Cl2 nak kena form, dia kena langgar dengan Cl lah. Dia jangan langgar dengan O. Okay, ni kan dia facing the oxygen. Dia kan ada N, dia ada O, dia ada Cl kan. So the Cl need to be faced with Cl from NO2Cl, from this one. Dia tak boleh facing oxygen, dia tak boleh facing this oxygen. Dia kena face the Cl. Baru kita kata proper orientation. Ini dia face dengan O. So what happens is that dia collide tetap collide. It's just that dia will not produce product. That means dia mungkin bounce back ke ataupun dia distorted ke later on kan. So but those will not produce product because the orientation is not correct. But the effective collision, dia produce product because they collide in proper way ataupun proper condition. Okay, so you nampak dia CL bertemu CL and they collide, and at this point of time the bond will be formed, and this bond CL dengan N ni will start to break. And this one break, and inilah produk yang kita nak kan based on the equation here. So this is what we call effective collision.
Madam,
Yeah.
let's say dia dah ada proper orientation kan, tapi dia punya activation, dia punya energy is not that high. So is it possible to?
Tak boleh. Tak boleh.
juga.
Okay. Dia kena dua-dua. Okay, kalau maksudnya begini bila dia cakap effective collision, provided that the EA, the energy is already sufficient lah. Okay, bila dia consider effective collision, maksudnya kita assume that the second rule tadi dia dah obey lah. Dia kena obey that two syarat tu simultaneous, maksudnya at once, serentak. Dia tak boleh salah satu. Okay, proper orientation and sufficient energy. So since dia consider ni as effective collision, kita boleh assume that this molecule has enough energy. Okay, and they collide in proper orientation. Okay, alright. So this is in terms of effective dengan ineffective collision. Kejap lagi kita nak tunjuk in terms of sufficient energy. Dia tunjuk each one lah. Okay. Okay. Alright. So settle for the orientation. Now we move on to energy, the activation energy. You guys know already apa itu activation energy. Okay, yang bukit tadi. And in fact, in semester 1 also you have been introduced to activation energy. Okay. The activation energy is the minimum energy which must be overcome for a reaction to occur. The minimum energy, kalau you ada extra energy melebihi that EA, of course lah you akan be able to overcome. Okay, contohnya you nak ambil degree in pharmacy. Okay, in pharmacy, the requirement, dia punya CGPA requirement will be 3.5. Okay, alright. So dia punya minimum energy will be 3.5 lah. Tapi kalau you adalah 4 flat ataupun 3.9, of course lah you ada more energy to overcome the barrier ataupun the EE. Okay, that's why they use the term here used is minimum. Okay, so dia kena ada minimum, dia boleh overcome the EE. Right, so like I said, energy is required to break the bond or of reactant in order to form a product, and it is provided from the kinetic energy of the molecules before the collision. Molecules are constantly moving at various speed. Okay, all right, so that energy is used to break and form the bond, and it is provided from the kinetic energy of the molecule itself before the collision take place. Okay. Alright. The kinetic energy is converted to potential energy as the molecules are distorted during the collision. So the moment they collide, the kinetic energy is being transformed into potential energy. Okay, it's being transformed to potential energy dekat situ. Because product dengan reactant now have different energy dekat situ, ya. So the product, reactant, okay, they both have different potential energy.
Madam,
bond, yes.
Distorted tu basically waktu diorang collide tu
The molecule are distorted during the collision. Maksudnya distorted as in it's no longer the same as the original one. It's either dia form product ke ataupun dia terputus, dia cantum balik ke. That is what it meant by distorted. Okay, tapi dalam case ni distorted is like they produce product lah. So it's no longer the same as the original one. Itu maksud distorted. Okay, alright. So bond in the reactor molecules are broken. New bonds are formed in the product molecule. Okay. Distorted. Okay. The EA and activated complex is illustrated in energy profile diagram. Okay, ini kita nak introduce the transition state ataupun activated complex. The energy profile diagram. Okay, and this is the graph. Okay, so this is the EA. Ni EA. Okay, ini energy reactant. This is the reactant. This is the product. Okay, ini kita boleh tahu that it is an exothermic reaction. Because why? Because the energy of the product is lower than the energy of the reactant. Itu characteristic of exothermic reaction. Saja je lah, dia tak suruh tanya pun, tapi kita boleh identify. Since kita dah belajar kan, kita identify lah. Okay, EA is this one. From the reactant to the top of the the top of the mountain nak cakap gunung kan, bukit ni yang paling tinggi. Okay, dia punya tips dia tu. So this is what we call tempat ini dipanggil transition state. Okay, itu dipanggil transition state. And then dia punya species yang present at this transition state is what we call activated complex. Jangan confuse, transition state adalah keadaan sementara di mana dia ni duduk at the highest, at the peak lah, the peak pada EA tu. Itu transition state. Dia adalah tempoh sementara, transition. Okay, and species yang ada pada ketika transition state tu is what we call activated complex. Okay, kadang-kadang kita panggil transition state juga untuk this one. Kadang-kadang kita panggil activated complex. It's actually the same thing lah. Okay.
Adam.
Yeah.
Yang dekat transition state tu basically dia punya energy is the highest lah kan?
Yeah. Okay, the highest. Sebab dia dekat peak ni, dia paling tinggi, dekat top sekali ni. Okay, dia the highest. Nanti kita akan tengok dia punya characteristic of this transition state. Okay, alright. So EA is the difference in energy between the reactants and the transition state. EA is the difference in energy between the reactants and the transition state. So this is EA lah. Betul lah juga statement dia tu. Okay, from the reactant to the transition state kat situ. Large value of EA indicates slow rate of reaction and vice versa. So you boleh imagine tak, the higher the EA, right, more energy is needed to overcome the bukit, to overcome the EA. Maksud imagine kalau tinggi bukit dia tu, okay, that means more energy is required in order to overcome the EA. That means less molecule will have that energy nak overcome this bukit. So you boleh imagine in terms of rate of reaction, the rate of reaction will be lower. Okay, it will be lower sebab EA kan dia ada dua faktor kan. Satu orientation. Tapi kalau orientation betul, EA dia tak boleh, dia tak cukup energy to overcome the EA. Sama juga. Tak boleh juga produce product. Dia tak produce product, what happen to the rate of reaction? Rate of reaction is counted, is calculated based on the number of product produced. The number of successful collision. And successful collision is based on the number of product produced. So kalau tak boleh nak produce product, that means rate, what happened to the rate? It will be lower kan? Okay? So it depends. Okay, sorry, EA is very important in determining the rate of reaction. Okay, whether they proceed slower ataupun faster. The rate of reaction is solely determined by the height of the EA. See, dia siap cakap solely dia tu. Bergantung sepenuhnya kepada ketinggian EA tu sendiri. The higher the EA, the more energy is needed to overcome the EA. Okay, and to produce product. EA is needed to form the final product lah. So the arrangement found on the top of the potential hill is called the transition state or activated complex, like I said just now. Okay, so these terms are used interchangeably. Okay, so what are the characteristic of this activated complex ataupun transition state? Apa karakteristik dia? It's the maximum energy. Paling tinggi kan? The maximum. It has a maximum energy. Kalau dah maximum, that means it is extremely unstable. That's why nama dia transition state. Dia hanya present sekejap saja. Okay, tapi dia kena ada. Dia tak boleh tak ada. Dia kena lalu dia. It's just that dia hanya available ataupun present only a short period, okay, before it can produce product. Okay, alright. Exists at instant, okay. So dia jadi sekejap saja, more potential energy than either the reactant or the product. So dekat peak ni, the potential energy is the highest. Yelah, you tengok lah ni kan graph, you graph kan. So dia paling tinggi guys tu. So the potential energy is the highest. The highest energy, ni okay. Bonds in reactant are partially broken and the new bonds in product are partially formed. So this is another point that you have to take note. Okay, all right. Other than these two, what are the one that is the karakteristik yang important to describe this activated complex is that during the formation of activated complex, the bonds in reactant are partially broken and the new bonds in product are partially formed. Okay, ataupun in short, new bonds are about to form and old bonds are about to breed. Okay, so ni kena ingat lah kalau dia tanya karakteristik of the activated complex. At the transition state, the reaction can either proceed forward or backward to give product or reactant respectively. Jangan ingat serabut lah. Okay, jangan ingat you confirm you dah ada dekat sini on top of the world, you confirm akan dapat apa yang you nak, which is produce product. Not necessarily. You can fall back to your original place. Okay, so bila dah berjaya tu, dah berada di tempat, di puncak dunia tu, janganlah sombong. Okay, tiba kan. So janganlah sombong, so be humble. Okay, sebab dia ibarat roda, you may come back to your old ataupun original position dekat situ. Okay,
Madam,
tiba.
yang apa tu? Dia katakan tadi dia boleh form new bonds ataupun broke the bonds kan. So basically dia depends on energy yang kita nak provide tu lah kan.
Ya. Okay? Ya. So kalau energy tu awal-awal dah tak cukup, memang tak cukup lah untuk nak break the bond, nak form the bond. So memang dia tak lepas pun, tak naik pun bukit ni. Ada case dia cukup naik ke atas ni, cukup. So nak start ni, tapi somehow dia tak jadi juga. Okay, dia tak jadi juga, dia still not forming the product dekat situ. So that's why the point ni at the transition state, the reaction can either proceed forward or backward to give product or reactant respectively. Okay, so ada that possibility, still ada juga. Along the way somehow tiba-tiba you know the condition is just not right lah somehow kan. Dia tiba-tiba temperature drop ke apa kan. Dia fall back lah to its original position. Okay, in a reaction that occurs in 2 or more steps, each step has its own transition state. The reaction intermediate correspond to an energy minimum between transition states. See, nampak ada camel pula kat sini, ada unta pula kat sini Selalunya, okay, commonly kita punya profile energy diagram ada satu je bonggol. Tapi ni ada 2. Jangan terkejut, ada 2 Boleh ada 3, 4, 5 dan seterusnya. Okay, so maksudnya kalau we have more than 2 EA, okay, you can imagine that the reaction has an intermediate. Okay, ada intermediate. Intermediate maksudnya A plus B, kata kalau dia jadi C plus D. And then C plus D, dia jadi, okay, tak nak. Dia dah, okay, A plus B becoming C plus D kan. So the final product is C plus D. But along the way, in order to produce C plus D, somehow dia jadi X plus Y dulu. Okay, dia jadi X plus Y. So this is what we call intermediate. And then dia in a reaction that occurs in 2 or more steps. Because not all reaction, remember thermochemistry last time? Okay, yang kita kena lalu steps untuk nak banyak step in order to finally come to our final product kan. Kan kita banyak step kan. So setiap steps tu, you tahu lah, ada its own energy profile diagram. Okay, ingat tak yang kita cancel, Hess law last time? Those are intermediates. Okay, those are intermediate yang kita cancel tu. So, how do we represent them in terms of energy profile diagram? So, this is one of the way. Okay, alright. So, maksudnya A plus B jadi X plus Y dulu. So, this is the energy profile diagram. So, dia ada its own EA, guys. Dia ada its own EA. So, this is what we call intermediate. Intermediate means these later will be used as reactant to form the final product. So lagi satu EA. Okay, lagi satu EA. Tapi bila kita nak determine A, B kepada C, D, ini exothermic ke endothermic? Macam biasa, kita kena check the reactant, dia punya energy lower ke ataupun higher than the product. The energy is higher ataupun lower than the reactant. In this case, this is an exothermic reaction. Kalau overall, I'm talking about overall AB jadi CD. Tapi kalau kita boleh pecahkan, kita boleh check AB jadi XY. Is it exo, endo, guys? AB jadi XY.
Endo.
It is
Endo.
XY, CD. Exo. Okay? So yang endo ni lah yang selalunya leceh sebab dia punya EA dia tinggi. EA dia tinggi. Okay? Apa ni? Alah, ada pukul 6 lah. Sekejap tengok banyak lagi ke? Okay. Alright, jom kita habiskan yang energy profile diagram ni. Okay, and then the rest kita continue next week lah. Sikit lagi dari 2-3 slides lagi. Okay. Consider the reaction between NO2Cl and Cl to give NO2 and Cl2. Okay, contoh. Alright, so this is the reaction. Apa ni? Okay, this is the energy profile diagram. Okay, so this is the reactant. Kita pun label. And this is the EA. That means, remember macam mana you nak label the EA. It's from the reactant to the highest peak. Ataupun to the transition state lah. That will be the EA. Okay, we subject to this one. Kita nak produce NO2Cl2. This is the EA of forward reaction. Nak produce NO2 and Cl2. Did you know that we can also have EA reverse? EA reverse maksudnya produk nak jadi reactant balik. So, maksudnya produk tu dia pula jadi reactant. Dia tukar jadi reactant. So EA reverse you macam mana you nak label your EA reverse? Remember dia from reactant to the highest peak. So tadi produk tadi tu digunakan balik to produce nak reverse reaction kan? That means the product to the highest peak, this will be your EA reverse. Okay, EA reverse. So apa yang you boleh conclude from this? Your EA forward is still the highest compared to your EA reverse. EA forward you tu tinggi, lebih besar daripada your EA reverse. Ataupun EA reactant you is larger compared to your EA of your product. Okay, when you minus these two, you akan dapat delta H. Okay, you akan dapat delta H. Delta H you should be positive value lah. This is an endothermic reaction. This is a characteristic of endothermic reaction. You punya forward EA forward you is larger compared to your EA reverse. Characteristic of endothermic. Okay, make sure that you are able to describe in terms of EA forward dengan EA reverse. Yang you tahu selalunya the energy of the reactant dengan energy of the product kan. Kita boleh tahu di endo ke exo. Kalau product is higher than the reactant, that means it is endo. But you should also know that in terms of EA, okay, if it is reverse for endothermic reaction, it is lower than the EA of the forward reaction. Okay? And vice versa lah. And vice versa. So imagine kalau you ada exothermic reaction. Macam ni. Exothermic reaction. Okay, so this will be your EA forward. Buruk lah tulisan tadi. This will be your EA reverse. EA forward ke depan pergi ke sini. So EA forward you lebih rendah daripada EA reverse you. This is for exothermic guys. And this one is for endothermic. Okay? Alright. Okay. EA reactant. Oh, I see. Okay. Right. So EA reactant is also known as EA forward, guys. EA reactant is also known as EA forward. EA product is also known as EA reverse. Okay. This one lah. Yang ni. Okay. Like what I've shown to you just now. This is exothermic. This is an endothermic reaction. Okay. Delta H has no influence on the rate of reaction. Okay. Alright. Okay. Sketch energy profile diagram and activated complex for the reaction below. Cuba try sekejap. Bagi saya 2 minit. Bukan saya, awak cuba try. Sebab ni macam semester 1 punya ni kan. Cuba try. Roughly sketch the energy profile diagram. Okay. Okay. Activated complex tu kita nak determine later. Roughly sketch nak dapat the idea of it. Delta H is given. Okay, it's negative value. Okay. Make sure that you label everything that need to be labeled. Jangan miss out the label. Contohnya exist. Exist tu markah free je. And then bentuk graph. This is an exothermic or endothermic graph, guys?
Exothermic.
So,
Tolonglah jangan salah kat situ. Sebab situ je bila you satu markah. Kita akan tengok you punya produk tu lebih rendah ke lebih tinggi daripada you punya reactant. Sepatutnya it should be lower than the energy of the reactant. Kalau terbalik, salah, hilang satu markah. Okay, alright, jom. Okay, so this is how your apa nama ni? Energy profile diagram should looks like. Ini pun saya nak komen, mungkin drawing dan tak boleh macam ni, dia tak boleh terjongkit. No, kena flat guys. Okay, tak boleh terjongkit. Ini pun the EA is missing. Biasalah kan, tertinggal-tinggal. Okay, EA. Dah lalang belajar tadi kan. So here, okay, katakanlah this is your EA forward. Okay, right. This will be your EA reverse. Sebab kita dah baru belajar tadi. Apply lah. Okay, EA reverse. And then what else? Okay, this will be your transition state. And then delta H, make sure that you label the delta H. Delta H is very important, guys. Okay, make sure you tahu beza antara reactant dengan product. This will be your delta H. So, letakkan the value lah. Okay, and then this potential energy and this is the progress of reaction. Okay, done. So this is an exothermic reaction. Settle. Okay, next. Moving on. Dia nak apa? activated complex. Kena draw. Okay, you kena draw the activated complex. Kat sini yang student dia ada masalah sikit. But you kena imagine. Ingat, activated complex, dia orientation kena betul. Okay, alright. So, this is how the activated complex looks like. Dia punya tips for activated complex, you nak predict the activated complex is based on the equation yang you ada ni. Okay, alright. So, you have CO and you have NO2. Okay, you kena tahu siapa yang kena bertemu siapa. Okay, alright. NO2 ni nanti dia jadi NO. CO ni nanti dia ambil oxygen from from NO2. So maksudnya dia punya oxygen tu kena come closer. Maksudnya kena facing one another lah. Okay, kena facing one another. So itu kita tahu sebab kat situ nanti the bond will be formed. The bond will be formed. Okay, and then the rest tu the bond will be NO2 ni nanti dia akan start to break. So macam mana you nak represent the activated complex yang ada bond to be formed, bond to be broken. Macam ni lah. Okay, this is the CO kan tadi kan? This is the CO and this is the NO2 just now. Ini dia punya reactant dia tu. So macam mana kita nak make sure that dia facing one another? Yeah. Okay, alright. So C tu kena, sekejap. Sorry. Saya pun dah tersalah sebab C ni dia dengan O je kan. Dia dengan O. So sebenarnya O ni dia akan melekat dekat C sebenarnya. Bukan melekat kat O Minta maaf. Cuma bila dia combine ni dia akan jadi CO2. Tapi sebenarnya bila dia langgar, dia akan langgar dengan C. Dia akan form bond dengan C dekat situ. Okay, alright. So this one NOO ni kan dia NO2 kan. This one is CO kan. So this one nanti dia akan start to break. One of the oxygen will start to break. And then this oxygen dia akan attracted to C. Maksudnya when dia langgar dengan C, dia akan start to form the apa nama ni? The bond lah. Jadi CO2. Ini chemical bonding lah last time. Okay, dia tak akan bertemu dengan O dia akan bertemu dengan C. C will become the central. Okay. So kena reverse sikit. Kenapa? Mungkin ada soalan nak tanya. Madam, kenapa dia tak langgar dengan O? Dia tak boleh langgar dengan O. After all, O dengan O kan dia repel lebih kan. So dia sebenarnya akan langgar dengan C. Sebab CO2 macam mana ubah CO2? Macam mana you draw CO2? Macam ni kan. So C yang pegang both of the oxygen. Okay, alright. So this is how your activated complex looks. Alright. So that is all guys for today. Okay, so we have few others. Okay, alhamdulillah apa yang kita dapat cover tu dah cukup banyak dah. So kita ada 123 slide. So now kita 81 slide 81. So hopefully next week kita be able to habiskan lah Kenalah juga habiskan. Okay. Alright. So itu saja for today. Any question?
Clear, madam.
Okay. Tak ada ya? Alright. So bagus, clear. Okay, so that is all. Thank you everyone for your attention. Assalamualaikum. Bye-bye.
Madam.
Thank you, madam.